We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel the liftoff. The clock has started.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
Okay, I'm separated from the spacecraft. Getting my feet out. Okay, I'm out. Really looks funny out there in my glove out there, Jim.
Jimmy 4, get back in.
Okay.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 49 of the Space Rocket History Podcast. I recommend listening to episodes 47 and 48 before you listen to this episode. And now, Gemini Systems Design, 1962. Last week we stopped at the end of 1961 when contractors were authorized to begin work on using the Titan II in the Mercury Mark II program. I want to begin this week on January 3rd, 1962, when Gemini became the official designation of the Mercury Mark II program. The name had been suggested by Alex Nagy of NASA headquarters because the twin stars Castor and Pollux in constellation Gemini seemed to symbolize the program's two-man crew, its rendezvous mission, and its relationship to Mercury. So, from now on, the Mercury Mark II program will be called Gemini. In addition to the name change, the Manned Spacecraft Center was undergoing a big reorganization and move from Virginia to Texas. On January 15, 1962, Director Gilruth announced the formation of separate Mercury, Apollo spacecraft, and Gemini project offices. The old engineering division was abolished. Its staff was divided between Gemini and Mercury offices. As the year progressed, NASA Administrator James Webb officially announced that a new Mission Control Center for manned spaceflight would be established at the Manned Spaceflight Center in Houston. You may recall Project Mercury flights were controlled from the center at Cape Canaveral, but these facilities were inadequate for the more complex missions envisioned for the Gemini and Apollo programs. The control center was expected to be operational in 1964 in time for the Gemini rendezvous flights and to cost about $30 million. Later in 1962, NASA awarded a contract to International Business Machines Corporation, IBM, to provide the ground-based computer systems for Project Gemini and Apollo. The computer complex would be part of the integrated Mission Control Center at the Manned Spacecraft Center in Houston. Now let's examine the progress of Gemini systems design in 1962. We want to begin with the launch vehicle. In January, the Manned Spacecraft Center, MSC, completed a formal statement of work for the Titan II, along with a request to buy 15 launch vehicles. The statement of work included many additional changes from the original agreement made between NASA and the Air Force only a month earlier. The MSC group realized that fitting a Titan II for Gemini would require new systems to ensure the safety of the crew during countdown and launch. This included specifically a system to detect existing or impending malfunctions and to signal them to the crew. Undaunted, the Air Force had Martin Company under contract by January 19, 1962. And on a positive note, the Air Force successfully launched the ICBM version of the Titan II on March 16th. This was the first successful test, and it flew 5,000 miles over the Atlantic. Now moving on to the rendezvous vehicle. By the end of January, MSC had evolved a fairly clear idea of the rendezvous techniques it planned for Gemini, and had prepared a statement of work for Atlas Agena. This was forwarded to Marshall on January 31st, along with a request to buy 11 Atlas Agenas. Atlas as launch vehicle for Agena was no problem since it was already being used for that purpose on other programs. But Agena needed several changes to adapt it to its rendezvous role, such as radar and other tracking aids, a restartable engine, a better stabilization system, more elaborate controls, and a docking unit, to name a few. Fortunately, time was not so pressing for Atlas Agena as it was not scheduled to launch until later in the program. MSC wanted the first target vehicle delivered in 20 months, or around September 1963. On May 1st, the Air Force Space Systems Division awarded a contract to Lockheed for 8 Agena vehicles to be modified as Gemini target vehicles. Mission requirements were to 1. Establish a circular orbit within specified limits, 2. Provide a stable target with which the spacecraft could rendezvous and dock, 3. Respond to commands from either ground stations or the spacecraft, 4. Perform a complex series of orbital maneuvers by means of either real-time or stored commands, and 5. Provide an active orbit life of 5 days. Now let's move on to the spacecraft systems. You may recall that McDonnell Company was selected as the primary contractor for the Gemini spacecraft. Of course, McDonnell couldn't do all the work in-house, so they subcontracted the work to other companies that specialized in particular areas. For instance, in February of '62, McDonnell gave AI Research Manufacturing Company the subcontract to manufacture the environmental control system. The system was patterned after the environmental control system used in Project Mercury, which was also built by AI Research. The Gemini environmental control system consisted of suit, cabin, and coolant circuits, and an oxygen supply, all designed to be manually controlled whenever possible during all phases of the flight. The primary functions of the environmental control systems were controlling suit and cabin atmosphere, suit and equipment temperatures, and providing drinking water for the crew and storage or disposal of wastewater. Later in February, McDonnell gave Rocketdyne a contract to build the liquid propulsion systems for Gemini. 2 separate systems were required. The first was the Orbital Attitude and Maneuvering System, abbreviated OAMS, and the Reaction or Re-entry Control System, abbreviated RCS. The Orbital Attitude and Maneuvering System, located in the adapter section, had 4 functions. Number 1, providing the thrust required to enable the spacecraft to rendezvous with the target vehicle. Number 2, controlling the attitude of the spacecraft in orbit. Number 3, separating the spacecraft from the second stage of the launch vehicle and inserting it into orbit. And number 4, providing abort capability at altitudes between 300,000 feet and orbital insertion. The OAMS initially comprised 16 ablative thrust chambers, 8 25-pound thrusters to control the spacecraft attitude in pitch, yaw, and roll axes, and 8 100-pound thrusters to maneuver the spacecraft axially, vertically, and laterally. The re-entry control system was located forward of the crew compartment in an independent RCS module. It consisted of 2 completely independent systems, each containing 8 25-pound thrusters, very similar to those used in the OAMS. Of course, the purpose of the re-entry control system was to maintain the attitude of the spacecraft during the re-entry phase of the mission. In early March, McDonnell subcontracted Thiokol Chemical Corporation to provide the retrograde rockets for Gemini. The primary function of the solid propellant retro rockets, 4 of which were located in the adapter section, was to decelerate the spacecraft at the start of the re-entry maneuver. There was a secondary function, and it was to accelerate the spacecraft to aid its separation from the launch vehicle in case a high-altitude suborbital abort was required. On March 19th, McDonnell gave Advanced Technologies Laboratory the subcontract to provide the Horizon sensor system for the Gemini. 2 Horizon sensors, one primary and one standby, were part of the spacecraft's guidance and control system. Their purpose was to scan, detect, and track the infrared radiation gradient between Earth and space, to provide reference signals for aligning the inertial platform, and error signals to the attitude control and maneuver electronics for controlling the spacecraft's attitude and its pitch and roll axes. On March 21st, McDonnell awarded a contract to Motorola to design and build the digital command system for the Gemini. The system was used to receive digital commands transmitted from ground stations, decode them, and transfer them to the appropriate spacecraft systems. The system was used to receive digital commands transmitted from ground stations, decode them, and transfer them to the appropriate spacecraft system. Later in March, McDonnell subcontracted General Electric to design and develop fuel cells to provide power for the spacecraft, and in April, McDonnell awarded a contract to IBM to provide the computer system for Gemini. The digital computer was the heart of the spacecraft's guidance and control system. Supplementary equipment consisted of incremental velocity indicator, which visually displayed changes in the spacecraft's velocity, the manual data insertion unit, and that was used for inserting data into and displaying readouts from the computer, and the auxiliary computer power unit, and that was used to maintain stable computer input voltages. In addition to providing the computer and its associated equipment, IBM was also responsible for integrating the computer with the systems and components it connected with electrically, including the inertial platform, rendezvous radar, time reference system, digital command system, the data acquisition system, attitude control and maneuver electronics, the launch vehicle autopilot, the console controls and displays, and the aerospace ground equipment. Which brings us to the ejection seats. The ejection seats were to provide the crew a means of escaping from the spacecraft in an emergency while the launch vehicle was still on the launch pad, or during the initial phase of powered flight up to 60,000 feet, or in case of a paraglider failure after re-entry. In addition to the seat, the escape system included a hatch actuation system to open the hatches before ejection, a rocket catapult to propel the seat from the spacecraft, a personal parachute system to sustain the astronaut after his separation from the seat, and survival equipment for the astronaut's use after landing. On May 29th, representatives of McDonnell, Weber Aircraft, the Gemini Procurement Office, the Gemini Project Office, and the U.S. Naval Ordnance Test Station concluded their plans for developing testing of the ejection seat. The requirements peculiar to Gemini spacecraft, in particular off-the-pad abort capability, caused the plan to stress testing from a stationary tower early in the test program, because they didn't know if it was going to work. Tower tests began July 2nd. They were to be followed by rocket sled ejection tests to investigate simultaneous ejection with open hatches at maximum dynamic pressure. Sled tests began on November 9th, before tower tests had been completed. Now let's move on to the most important Gemini component, the astronauts. In April, NASA announced that applications would be accepted for additional astronauts until June 1st. NASA planned to select 5 to 10 astronauts to augment the 7-member Mercury astronaut team. The new pilots would participate in support operations in Project Mercury and would join the Mercury astronauts in piloting the two-man Gemini spacecraft. To be chosen, the applicant had to 1. Be an experienced jet test pilot and preferably be presently engaged in flying high-performance aircraft. 2. Have attained experimental flight test status through military service, aircraft industry, or NASA, or have graduated from a military test pilot school. 3. Have earned a degree in physical or biological sciences or in engineering. 4. Be a U.S. citizen under 35 years of age at the time of selection, 6 feet or less in height, and 5. Be recommended by his parent organization. Pilots meeting these qualifications would be interviewed in July and given written examinations on their engineering and scientific knowledge. Selected applicants would then be thoroughly examined by a group of medical specialists. The training program for the new astronauts would include work with design and development engineers, simulator flying, centrifuge training, additional scientific training, and flights in high-performance aircraft. On September 17th, Director Gilruth of the MSC introduced the 9 men who had been selected for the flight crew training program. Of the 9, 4 were from the Air Force, 3 were from the Navy, and 2 were civilians. From the Air Force were Major Frank Borman and Captains James A. McDermott, Edward H. White, and Thomas P. Stafford. The Navy volunteers were Lieutenant Commanders James A. Lovell and John W. Young, and Lieutenant Charles Conrad. The 2 civilians were Neil Armstrong and Elliot M. C. Now that we have our astronaut candidates, let's consider the systems required to support them. In order to monitor the astronauts' health at all time, MSC's Life Systems Division proposed to measure 7 parameters for determining crew condition during all Gemini flights. These were, in order of priority, blood pressure, with electrocardiogram and phonograph serving as first and second backup, electroencephalogram, respiration, galvanic skin response, and body temperature. To keep the astronauts fed, food and zero-gravity feeding devices were to be provided by the U.S. Army Quartermaster Corps' Food and Container Institute, under the direction of MSC's Life Systems Division. Whirlpool Corporation was contracted to provide the Project Gemini food and waste management system, consisting of water dispensing, food storage, and waste storage components. To clothe the astronauts, B.F. Goodrich was initially contracted to deliver a prototype partial wear, quick assembly, full pressure suit to MSC for evaluation by the Life Systems Division. The partial wear feature was required because of the long duration missions planned for Gemini. The suit included detachable sleeves, legs, and helmet. The final Gemini system I want to consider today is the paraglide recovery system. It is the most controversial and the one real exception to Gemini's smooth progress through 1962. Here's an audio clip explaining the system.
The Gemini paraglider program was an attempt to produce a land landing system for Gemini. In the beginning, NASA hoped that on the manned Gemini missions, instead of splashing down in the ocean and having to have a whole Navy fleet to fish you out, that they would actually be able to bring the Gemini back into a landing on a runway, or at least on the dry lake bed in California.
A dart-shaped inflatable wing called a paraglider will free him from the uncertain drift of a parachute driven by the winds and give him the relative precision of maneuverable flight as he nears the Earth's surface, combined with the capability for a gentle touchdown.
TTV-1 is one of these 2 tow test vehicles that flew landings at Edwards Air Force Base in 1964. Really just a simple steel boilerplate of the external shape of the Gemini reentry module was towed behind a truck and then later towed behind an aircraft with the wing and then released and glided in for a landing on the lake bed. It proved to be too difficult a challenge. It just couldn't be developed in time. It took too long. It proved to be too challenging. And so by the time they were flying these land landings with a tow test vehicle, NASA had already given up on it. It already canceled it as a regular part of Gemini.
The paraglider was controversial from the beginning. Although Gemini Project Office and Chamberlain in particular stoutly defended the concept, others in MSC had strong doubts. The Engineering and Development Directorate under Max Faget had been notably cool to the idea from the outset. The key question had been whether the deployment reliability of a single paraglider would equal that of a main and backup chute system. The long-time efforts of Langley's Francis Rogallo, inventor of the paraglider, to sell his concept had been repeatedly countered by the argument that parachutes had proved they could be relied upon to recover spacecraft. Instead of wasting time on untried concepts, Faget's group favored efforts to improve parachute technology to permit land landing. They advocated using a new form of parachute that could be steered with landing rockets to cushion the final impact as the spacecraft touched down. Another source of opposition to the paraglider was the Flight Operations Division under Christopher Kraft. Questions of reliability here took second place to the concern for the operational problems posed by the paraglider in the Gemini program. For Kraft's division, using a paraglider and using ejection seats were two sides of the same coin. One required the other. Neither was reliable, and both promised immense practical obstacles to the safe return of the astronauts. Kraft himself urged on Chamberlain and later on MSC Director Gilruth his objections to both systems. The deciding factor may have been that the paraglider was simply not ready in time to use. It's a shame that with all the money, time, and effort spent, the paraglider yielded nothing for the Gemini program. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage spacerockethistory.com and clicking on the orange donate button or the Patreon link. Thanks.